right, let's get to that. So I should probably at some point tell you the name of this theorem. This theorem has a name. This is the real spectral theorem. And by the way, the set of eigenvalues, if you arrange them in order, is often called the spectrum. So and that goes back to spectroscopy, because one of the places where this was originally studied was in quantum mechanics, where we looked at linear operators on state space, and the eigenvalues were the observed values in spectroscopy. So spectrum goes back to that. This theorem is the real spectral theorem. There is a corresponding theorem for complex vector spaces and maps. And if you want to read about that, it's like chapter 6 in Insel, Spence, and Friedberg. And I have attempted to prove these things in previous incantations of my linear algebra course, but I never quite do all the details because they're lengthy. But actually, proving all the details of the Jordan form is also lengthy. So you gotta, what can you do? You only have so much linear algebra time. This here, like I said, is an example of why I think it should, why I think we should talk more about this in regular linear algebra, because it allows you to rotate coordinates and discover this is actually a hyperbola in disguise. But in any event, we have more than what we need for chapter 5 of O'Neill. So let's get back to it. Also, good news, we are studying the differential geometry of surfaces. And how many dimensions is a surface? No. You're going the wrong direction. 3, 4, and by, no. Take it back one. 2, right. So that means that we're looking at a 2-dimensional tangent space, which means that when we're looking at our transformations of 2-dimensional tangent space, we're looking at a linear transformation essentially from R2 to R2, which means that of this stuff I've told you about for the last hour and a half, we really only need the most basic, easy part of it, the part that applies to 2x2 matrices. But I think it's worth our time for you to appreciate sort of the larger story this fits into. And that's why I spent some time in here, because I think it's, if you haven't seen that already in your education and you're thinking about going to grad school, it is something you should see. All right, so we did. So this is chapter 5 of O'Neill, which is on the shape operator. I mean, that's one way to look at it. It's actually more than that. The shape operator really is just something we can construct that captures the geometry of the surface in its working. And from the shape operator, we'll learn that we can calculate the curvature of a surface or the mean curvature of a surface. All right? So what's the definition? So we're going to be thinking about a surface in the sense we defined technically in chapter 4. All right? And so let me just say that. Let M be a surface in R3. So that's going to be the case throughout everything I'm saying. So that means that we have a collection of patches which cover it. They're regular, right? All that jazz. Definition. If P is an element of the surface M, then for each vector in the tangent space at P to M, all right, here it is, the shape operator at the point P acting on V be equal to minus the covariant derivative in the v direction of the unit normal vector field at P, where u was equal to like partial x partial x partial u cross partial x partial v, right? It's the unit, it's the, oh, that's not quite correct. Excuse me, I gotta be careful here. That's not quite it. Where u is the unit normal. To m at P, right? So, I mean, what can you tell me about how would we construct the unit normal? I mean, it kind of depends on how the surface is given, right? There are two basic strategies. So, what are the two ways? So if we have x, right, from D subset of R2 to M, if we have that, if we have a patch, as we do usually, then we can construct the unit normal. How do we do it? How about this? 1 over the length of xu cross xv, right? Times xu cross xv, right? So the thing I neglected when I just glibly wrote it down, the cross product of the partials, is it has to be unit normal, right? You have to normalize it. Okay? And I'm supposing that the point P rests inside the part of the surface which is covered by the patch X, all right? So, you know, patches. What's the other way we can look at it? How about this? M is equal to G inverse of some constant, right? Like if M is a level surface, what's the unit normal? How about we do gradient of G divided by the length of the gradient of G, right? That would describe the unit normal from the other viewpoint. These are the two calculational techniques we have to calculate unit normals to a surface. But we can calculate the unit normal given a surface. And what would the covariant derivative of u in the v direction describe? I've lost my long piece of chalk. Oh, here it is. So this should say how the unit normal is changing direction in the v direction, something like that. I mean, u, it's a unit normal, right? So it's always got length 1. So whatever this is, it's just describing something about the change in direction of the unit normal on the surface, right? That's what this thing is doing. The reason that the minus is there, we'll see as we go on. It's kind of like that minus we have in physics for the gradient of the potential energy. It's put there for the sake of making something else positive. It's kind of like that. So I wouldn't read too much into the minus here. It's just a choice. All right. So what can we prove about this shape operator? Well, first of all, where is it mapping to? Well, I mean, so let's see. I'd like to argue that the shape operator at P is a mapping from the tangent space at P to M to what? So where is this? So this is my first lemma, is that its output is again in the tangent space. All right. Now that's not. we don't know that for sure, right? I mean, it could be in the normal space in principle, right? Because the covariant derivative in R3, it could go in the tangent space, or it could go in the normal space in general. But this little calculation, so this is actually a lemma. And so here's the proof. So of course we have u dot u is what? Is 1, right? It's the unit normal. And remember this identity? V on u dot u, how does it work out? This was like item 6 in the properties of the covariant derivative, remember this? So we do covariant derivative of v of u dot u plus u dot covariant derivative in the v direction of u again. But u dot u is what? This is 1, right? Which is constant. So what's this say? This says that the covariant, okay, well, what does it say? Oh, duh. So it says that this plus this is 0, right? Of course, this is, it's the dot product, so it's twice. And what does that say? If the covariant derivative of u in the v direction dotted with u is 0, if you put a minus here, what does it give you? So, the shape operator at P acting on V dotted with U is equal to 0. What's that say? That says that the no, I mean, it says that the shape operator V is an element of the perp, right? The perp to the span of, well, the normal space to P, the normal space to P of M, because the U, the normal space to P at M is the span of the unit, the unit normal, right? And if the shape operator is perpendicular to the unit normal, it's in the perp to the normal space, which is what, as we've discussed, it's the tangent space, right? Which is what we want. The image of the shape operator is, again, a tangent vector to the surface. Let me just say it more simply. If the shape operator's output is perpendicular to the normal, it must be tangent to the surface. Do we agree? Let me get out of my perpination of the argument. Okay, great. So now we have that the mapping is into the tangent space, right? The perp to the normal is the tangent space is the thing, right? Right. I mean, the definition makes the domain the tangent space, right? But this lemma proves that, in fact, it's a function from the tangent space to the tangent space. Which means we can ask other questions, like, is it a linear function? What do you guys think? I mean, that's my next proposition. The shape operator is, in fact, a linear transformation. It's a linear map on the tangent space. And in fact, I'd like to say more than that, although I'm going to try to do it, but, well, okay, fine. Let's do this first. So linear map. So what should we do what? We should look at let's let C be a real number, and let's let, I'm going to let X and Y be elements of the tangent, vectors in the tangent space, if that's okay with you guys. Maybe I won't. I try not to do that. I'm sorry. I just find, what do you guys want? Little v and little w. So let's look at SP of, say, CV plus W. What's that equal to? Definition minus the covariant derivative, right?
Yeah, it's SP, or no, you're doing not, are you proving linearity or are you proving?
Linearity. That's the proposition. It's a linear map. But it's essentially immediately true by properties of the covariant derivative, right? By properties of the covariant derivative on R3, we can pull C out.
Yeah. And then SPV plus SPW are gradient of VUFT.
Uh-huh. And so that's C times the shape operator acting on V plus the shape operator acting on W. And there you go. That proves that the shape operator is a linear map. The gradient, yeah, the covariant derivative of the unit normal in the W direction, and right. So let's see here. I'm going to go a little bit out of order of my notes, which means I'm kind of going off to the deep end. We'll see if this goes well or not. You guys help me out if I get stuck, right? I think we can argue with our current technology that this is in fact a map for which the matrix is a symmetric matrix. All right? Now, so what would it, how would we capture the, if the matrix of a linear map is symmetric, what would that mean about the map directly? You know, like how would we, you know, this is something I should have thought about before, but my question for you is just sidebar. Suppose T of X, right? Or let's say T of V is equal to AV, and A transpose equals to A again. What does that condition mean about T itself? What does the symmetry on the A mean about T? Like, what does that give me? I think it's something about the dot product, all right? So let me try this out. What happens if we do like T of V dot W? What's that equal to? That's equal to AV dot W, right? But how do we convert dot product to a row column product? Remember, we do transpose times column vector. So this is, AB transpose W. In sock shoes, this is V transpose A transpose W, right?
Yes, but A transpose is just A.
Okay. So that's V transpose AW, which is, of course, V dot AW, which is V dot T of W. So
Is dot product in the matrix multiplication, or are you still dotting that?
the dot product is, so the dot product of a vector times another one is the transpose of the vector times the other one. So I don't know, I forgot what your question was. I think I answered it. I think this, all right, so like, I think this is if and only if, right? If you have T from say R, Rn to Rn, then the matrix of T is, this is unfortunate. Let me use S. If we have S from Rn to Rn, then the matrix of S transpose is equal to the matrix of S if and only if S of V dot W is equal to V dot S of W for all VW in Rn. I think that's a characterization that we could make. I mean, we just proved the we proved the forward implication, right? To prove the converse, how would you prove the converse? I mean, yeah. Suppose this condition is true for all V and W, right? Then by this calculation right here, that would mean that, well, so like this is equal to that, right? But this is equal to that. So if this is equal to that for all V and W, you can apply it to like the standard basis and get like EI transpose A transpose EJ is equal to EI transpose A EJ. And if that's true for all I and j, that means that A transpose, the ijth component of that, is equal to the ijth component of A. So yeah, I'm convinced that this is in fact a theorem. So what I'm trying to get at is we can prove, and sorry, having a brain lapse. Where is it? So I think we can prove that the matrix of S is symmetric with respect to some basis. Right. So this is, I've stated this theorem for the standard basis, but this is equally well true for like a non-standard matrix. Yeah, here I mean them to be vectors in Rn. So I want to use this theorem I just did to prove that the S, the shape operator, is symmetric, because the, I don't know, maybe I should just do it. I'm not sure this is really helping that much. Let's calculate the matrix of the shape operator, yeah? How should we do that? So how do we define the shape operator? What did we just say? SP of V, what was it equal to? Minus the covariant derivative of V in the U at P, right? And what's a basis for the tangent space, did we say? Remember, we can let the basis for the tangent space be what? Like partial, I mean, I said we could write it kind of this way. We could say it's partial partial U, partial partial V would be a kind of, that's one notation we could think about. But what I really mean by that is these guys, right? Those are the partial velocities. If I was to draw a picture, we're taking this point. So like one of these is partial x partial u. The other one is partial x partial v, right? The span of those gives us the tangent space of P. We spent some time proving that those are a basis, right? It took us like an hour. It's been a while on that. So to find the matrix, what would the matrix of this shape operator look like then in terms of these? Well, I should figure out what's SP of, partial x partial u. I don't know. I'm not sure what, like I told you guys, I'm kind of going off the deep end here. I'm not sure this is going to pan out for us. I mean, we'll eventually unravel these, but I think I have to build up some things before I get to it. I think we might do better overall in this course. Instead of using capital U for unit normal, do you guys want to try using a capital N for unit normal? I don't use capital N for anything else. Wouldn't that be easier to see? So let's try that out. Because I use V and I use the little u. The little u is the parameter, And I just think using big U for unit normal, in the same book we're using U1 and U2 and U3 for the Cartesian basis, it's really not a good notation. I've never found a good runaround from it, but it occurs to me just now, I almost never use N in this course. Why not use N? Oh, I remember why. N has a special meaning in like section 5.4. Sorry. Maybe I should make my U like more ornate. Would that help? Like no, that's worse. I don't know. There's no good. See, this is the trouble. This is the trouble. So fine, I'll be back to my stupid U. You're not stupid. It's just this U that's stupid. No, you're not. No, I'm sorry. I'll shut up. SP partial x partial v. And I know. So you look at these formulas, right? And you're kind of like, well, okay, lovely. What am I supposed to do with that, right? Because to find the matrix of that, I would have to express those as linear combinations of, you know what I'm saying? So I would actually have to say, let me just show you what's involved here. I don't know how to finish this calculation at the moment. Let me just show you. So like C1 partial x partial u plus, I'm going to bail on this here in just a second, C2 partial x partial v, C3 partial x partial u plus C4 partial x partial v, right? If I could find the constants, all right, C1, C2, C3, and C4, then I would know what the matrix of the shape operator looked like with respect to this basis, right? Because if this was the case, then that would tell me that the coordinate vector with respect to the beta basis of the image of the shape operator acting on the first basis element, which is partial x partial u, well, it would be C1, C2. Right? And if this was the case, then the matrix, the coordinate vector of the shape operator acting on the second basis element would be C3, C4. Right? And if I had all that, then I would have a stone cold formula for the matrix of the shape operator with respect to the beta basis. And it would be C1, C2, C3, C4 as I've written them here. Right? And that's you know, this is a lovely sentiment that I've expressed, but I don't have any sort of you ever get a package in the mail that you can't start gripping the tape on? It's kind of like that, like mathematically. Like, I don't know at the moment, given our current schemes, how do you actually calculate these constants, right? I don't know right at the moment, given what we know. So what I'm trying to say is direct computation of the matrix of the shape operator, it's kind of like not something we can see at the moment for an abstract example. Now, when we look at a specific concrete example, which I will very soon, then we'll actually find a formula, and then we can maybe do something concrete there. But at the moment, this is like sort of too much. But that said, the proof that the matrix is symmetric using this dot product theorem is actually not that bad. All right? So let me show you that. So even though I can't explicitly find this matrix and show you that it's symmetric directly, there's this kind of sneaky runaround argument using this. And so let me go through that argument right quick, because I want us to appreciate so here it is. Partial v of u dot x u is equal to partial u partial v dot xu plus u dot xuv. All right. Now, I think this right here is nothing more than just the product rule for the partial derivative with respect to v. I mean, this is just Calc 3 here. All right? Now, the next formula I have is more mysterious to me. I don't quite understand it yet. You guys tell me. The next formula I have here is that partial u partial v, I think that's equal to minus the shape operator acting on xv. Does that make sense? xv. Let's see here. What's the definition? The shape operator acting on xv should be minus the covariant derivative in the v direction, which in this case is xv, on u aha. So let's see, we have to, I need more board space to unravel that. think that makes sense actually. So let's kind of unravel it. XV, right, is partial x, partial x, partial v, partial x, right? Plus partial y, partial v, partial y, plus partial z, partial v, partial z, where big X has component functions x, y, z. These are functions of u and v, right? Functions of u and v. Now, how did we define, do you remember how we defined the covariant derivative? How did it go? What was our formula for the covariant derivative? So like if I had covariant derivative of, v in the w of the w of v, what would we say that was? It was like v of, what was it? V of w1, right? Partial x, right? Or I could write it u1 v of w2, right? u2 v of w3, u3, right? That was our formula for the covariant derivative. Let's put that into practice for this shape operator. We're looking at the shape operator of, what was it? Partial x, partial v, right? That's minus the covariant derivative, partial x, partial v of u. So how's that go? Right. Yes. So I guess we need to write u as, let's say, big U1, little u. See, this is where the notation is really kind of like stupid. I'm going to write it partial x. Just to right. Yeah, partial, exactly. Partial x, partial. So this actually means, I'll write it this way. Partial x, partial v acting on u1, just like you said. Right, and then that's in the u1 direction, which I'm going to write as partial x, right? Exactly. But this time u2 supposed to be a minus, right? All right. Now I'm claiming that is partial u partial v, right? Yeah, so I guess I'm going to have to expand this. I mean, this is literally partial x, partial v, partial x, partial y, partial v, partial y, partial z, partial v, partial z, all acting on the function u1, right? Partial x out here. That doesn't act on anything, it just rides along.
You get a constant of 0 and 0.
Well, this is you got to understand, this is a function of x, y, and z here.
Isn't there like a way to rewrite it where it's like you acting on that function, like
Yeah, I think that essentially the point here is that, and I admit the notation's a bit much, but this is actually what we would call minus partial u1 partial v in the partial x direction, and like the other two. And so like the next term is minus partial u2 partial v in the partial y direction, and minus partial u3 partial v in the z direction. And so this you could express alternatively as minus partial v on, you know, u1 partial x which is to say, so I'm really not giving you a proof as much as admitting what is rolled into the notation that's used over here. So minus s of xv is partial u partial v. I will say, if I had not had coffee before I started lecturing tonight, I would have not got through that. Yeah.
could you say that the partial big X partial B is a function on, like, there's property 3, covariant derivative f of z on acting on w is equal to f covariant of z acting on w.
Let's see here. I mean, I think you could rewrite this. You could pull these guys out and re-express this. You could re-express it as like little partial x partial v minus covariant derivative in the partial x direction of u minus partial y partial v covariant derivative in the partial y direction of u minus partial z partial v covariant derivative in the partial z direction of u. I mean, yes, you could do that. And I don't know if that would help you see things more clearly or not. But anyway, we have this now, right? SP of xv is minus partial u partial v. And so going back to this calculation here, what is this though, guys? What is u dot xu? Unit normal, tangent vector. This is 0. These are perpendicular. So this is straight up 0. But on the other hand, partial u partial v, you see now? See what partial u partial v is? It is minus the shape operator acting on xv. So we have minus the shape operator acting on SV dotted with XU plus oh, I better get my notes. I'm like, what? So that, great. This is equal to minus U dot XUV, great. And, oh, and then and basically then I say likewise, you can, by the same, just flipping the, same calculation as above, just flipping the roles of U and V, right? I could just as well take partial U of unit normal dot XV, and that would give me that S of XU dot XV equals to minus the unit normal dotted with XVU. But guess what? We're assuming that the patch is regular, that it's in fact smooth, so we can commute partial derivatives. And so this is equal to minus U dot XUV, which then is equal to minus S of XV dotted with XU. What does that show? So this, right, is equal to that. See, that's the condition that we need, right? That we can pull the dot product through, right? So this implies, by the theorem, that the matrix of the shape operator, with respect to the, this beta basis, is symmetric. But here's the cool thing. If you can show that there exists a basis for a linear operator, right? If there exists a basis for a linear map in which the matrix is symmetric, then the real spectral theorem says that the eigenvalues exist, they're real, and in fact there's an orthonormal eigenbasis with respect to that matrix. And it doesn't really matter that the matrix might not be symmetric with respect to some other choice of basis. The point is it's symmetric with respect to this choice of basis. So that means that the eigenvalues exist and are real, which means our shape operator has real eigenvalues. So we know what we're looking for now. So this is wonderful. That means we can expect that the eigenvalues of the shape operator are real. So let's look at some examples. Like, it's about time, right? So I'm omitting, there's a corresponding calculation I should have done for like partial U. It's the same song and dance, but with the partial derivative with respect to U, placing the partial derivative with respect to V. There may be a better way to give these arguments. I can't help but think there's a better way. But, all right, some examples. Let's see here. So, I think O'Neill uses sigma. Does he use sigma for the sphere? I say sigma is basically sigma is equal to my m, and it's given by length of P equals to R, that's a constant. So this is just a really, I mean, let me demystify this. So you're talking about M is x, y, z such that x squared plus y squared plus z squared equals to r squared, right? I mean, this is the sphere of radius r is what this is, all right? For this one, I can actually write a nice formula for the unit normal. Can you tell me what the formula for the unit normal is? At the point, well, just at a generic point. How about this? So I would like to just do the sum I equals 1 to 3 of like x, xi, ui, all right? But like, here's a picture. So suppose we had r equals to 2, right? So I'm suggesting, like, imagine that we use that for u, you know? What's wrong with that? It's not a unit normal, right? This would have length. So, I mean, this would be essentially just the point x, y, z on the sphere, right? Well, the sphere has length, has you know, distance r from the origin, right? So to make it into a unit vector, yeah, you want to make it have length 1, right? So you divide by 2 for my example, or for this generic one, r. Okay? And this is pretty great, because now we can calculate the covariant derivative in the v direction of u, and what's it going to look like? Remember our formula for covariant derivative? How did it go? Yeah, so v acts on, what was it? V acts on w1, which in this case is like x over r, right? Well, let me write it out. It's v on x over r, right? u1 plus v acting on y over r, u2 plus v acting on z over r, u3, right? But r is a constant, right? And so if v is like v1 partial x plus v2 partial y plus v3 partial z, then what's this work out to? So when partial x hits this, what happens? It gives you 1 over r, right? v1 partial r. And so if you look at that, we're going to get v1 over r u1 plus v2 over r u2 plus v3 over r u3. Did you guys see that? My bad. I was on the other board. Sorry to those of you who are not here. My apologies. It really didn't do much interesting though, right? It was very interesting. That's just not nice. So all I was saying was, we were looking at this picture and I was saying, so if we make this sort of the unit normal, it wouldn't work because it would have length 2. So we have to like divide by 2 to make it a unit normal. But then we divide it by r over here because we're looking at the r sphere. But the larger point here is what is this, though? See what this is? This is 1 over r times v1 u1 plus v2 u2 plus v3 u3. What is that? What is this right here? Right, it's like v. I mean, in the other notation, this would literally be v1, v2, v3. I mean, that is literally just, it's just v. So the formula we're looking at here is 1 over r times v. So what's the shape operator for the sphere? The shape operator at the point P acting on V is just equal to minus V over R. Because remember, the shape operator is minus the covariant derivative, right? Now, let's see here. I'll call that example 1. Example 2. What if we have a plane? Right? So a plane, let's say M, then what?
Is it like a plane like 3 or something, or is it like
Any old plane. Let's say that the normal is ABC. If the normal is ABC, and let's suppose that that's a unit vector, then the unit normal to the plane would be what? AU1 plus BU2 plus CU3, right? And this is a constant if it's a plane, right? It's a constant unit normal to a plane. So what's the shape operator? Minus the covariant derivative in the v direction of u at the point P. What's the covariant derivative of a constant vector? What did we learn before? The derivative of a constant? 0. So the shape operator on the plane, straight up, 0. How about a cylinder? So by the way, the difficulty we ran into, just straight calculating the shape operator in terms of a generic parameterization, this is a difficulty that has persisted since the early days of differential geometry. And what we'll see next time we meet is I'll talk more about there's special formulas due to Gauss that sort of work around that